Are you seeing my screen?
Yes, sir.
Okay. Today we'll be doing the first experiment, that is verification of Bernoulli's equations. So we'll be going through these topics. First of all, Bernoulli's equation, then what are specific weight and what are head. You know what head is, but you don't probably know what head is in terms of energy. Then continuity equations, then probably we'll look at some applications of Bernoulli's equations, then calculations and experimental setup. I will not do the calculations, I will just show you how to do it. And then piezometer, mm, and then these hydraulic and energy gradient lines, and then I will show you how to take the data and write the lab reports. So let's start with the Bernoulli's equation. Bernoulli's equation is something like this: P divided by gamma plus B squared divided by 2G plus Z equals to constant. Uh, have you seen it anywhere, these equations?
Yes, sir.
Where?
Sir, from internet, Google.
Okay. Do you know what it means? Okay. Bernoulli's
Not
equation.
exactly.
Okay, Bernoulli's equation is, it might look complex to you at first, but it is nothing but saying energy is conserved. It's simply saying energy is conserved. It's very simple, right? So let me give you one example where you might see law of conservation of energy. Uh, let's say you have this pendulum. You have this pendulum, and it's going from here to here, right? And then from here to here, from here to here, and then back here. So how many different types of energy does it have?
Two types.
Two types. What are those?
Potential energy, kinetic energy.
One is potential energy, one is kinetic energy. Perfect. So at the highest point, potential energy is what? Maximum, right?
Maximum is
Maximum, right? And kinetic energy will be zero,
zero.
because at this highest point velocity equals to zero. We know that kinetic energy equals to what? Half mv square. Half mv square. So kinetic energy will be zero, but potential energy equals to what? Mgh, right? Potential energy is something that you get for height. So here the height is like the highest, that's why the potential energy is maximum, mgh. So potential energy is maximum at this point. Potential energy is what? And kinetic energy is what? Kinetic energy is at this point
Highest half MB square.
maximum, and potential energy is equals to zero, right? Because it is at the lowest point or datum. Let's assume this one is a datum. So what is datum? Datum is basically the point from where you calculate the height. So at this point potential energy will be maximum, and kinetic energy will be zero, because velocity is zero, because it is turning. So when it start turning, its velocity gets zero, right? Now you know this concept of kinetic energy and potential energy. Let me introduce you one new type of energy. Let's say if it's a fluid that is flowing. Let's say if it is fluids that is flowing. So let's say these are the this is the fluid's directions. So as it's changing height, right? As it's changing height from here to here, its elevation is changing, right? It's as its elevation is changing, what will happen? Its potential energy will change, right? Now let's talk about kinetic energy. If the fluid speeds up, right? Like the velocity of the fluid, let's say here is 3 meter per second, and here velocity is 4 meter per second. If the fluid speeds up, the velocity of the fluid will uh, change. As the velocity changes, its kinetic energy will change, right? Kinetic energy will change, and this depends on bulk fluid motion. So what is bulk fluid motion? The bulk fluid motion is the fluid velocity that you actually observe. There is another type of fluid motion. Can you name that one? Anyone? There is another type of fluid motion. Can anyone name this?
No, sir.
Loss? No. Another type of fluid motion. The one that you are seeing is one. That is called the bulk fluid motion. There is another fluid motion. Can you name me all? Okay, let's assume that here you have some liquid, right? In a box. Do we have any velocity of the fluid here?
No, sir.
If I say there is some fluid motion, would you disagree with me?
No, sir. Atoms are.
Yeah, exactly. There is some motions of the fluid at the atomistic level, right? Uh, the bulk fluid motion of this box, let's say bulk fluid motion of the fluid here is zero, right? But there are some atoms and those atoms are randomly moving, right? As the atoms are randomly moving, we call that motions at atomistic level, or we have a name for it. What is that?
Sir, turbulent flow.
No, Brownian motion. I think you have heard the name Brownian motion, right?
I think we had that in college, but just couldn't remember the name of.
Yes, yes, you have. Uh, Today, what I will do is basically I will not teach you any new concepts today. I will be introducing the concepts and connecting them to your old knowledge. I could have just given you the equation and do some calculations and then tell you that let's just go to the experimental setup. But I will not do that. What I will do is basically I will connect your previous knowledge to this, how these are being applied in this Bernoulli's equation, right? Everything you know previous, like from your previous knowledge, I will be just connecting them, nothing else. So yeah, you already know about Brownian motion from college. It's a random fluid motion and it is not bulk and it is random fluid motion. The random fluid motion is created by the random motion of the what atoms, right? And it doesn't have any specific direction. So this is applying some forces on the walls, right? This is applying some forces on these walls, right? Now wherever some forces are applied, you are actually doing some works, right? So let's say the pressure of the fluid is P, and it has the capacity to do work P into V. So PV, V is the basically change in volume. If this is not like a rigid container, if this is not like a ceramic container, plastic container, but let's say it's a membrane that can move. Let's say it can move and it's a small membrane, then this Brownian motion has the ability to actually move the membrane to del V or V. So the work done by this fluid motion is PV, or pressure into change in volume, right? So do we have this type of motion in solid? If I, let's say this is a box and I kept some ball here, solid balls here, do we see that motion here?
No, sir.
Sir.
No, the motion or Brownian motion will be velocity will be zero. The bulk motion velocity will be zero. So we don't see that motion in these balls. So whenever we are talking about this ball or oscillating ball, that Brownian motion is not there. So that velocity will be zero. It can't do any work because of the pressure, right? But when we talk about this liquid, uh, besides having this bulk fluid motion, it has another additional motion that is within itself and it is completely random and it can do some work with that motion. That's why it has some energy or potential to do work, right? So now for fluids, how many different types of energy are there? One is elevation energy, right? elevation is basically the one due to height difference, right? This is similar to this, like potential energy. One is elevation, another one is kinetic.
Kinetic energy.
Kinetic is basically same as this half mv square. For fluid it is same half mv square, right? Another one is kinetic, and another one will be pressure, right? Another one will be due to pressure, right? So if I, and total energy is always what? Total energy is always conserved, right? What did we say at the beginning of this class? Is energy is always conserved no matter where. So total energy is conserved. Let's say some of them will be constant. It's basically same as this. Here only two types of energy were conserved. Here we will be seeing three types of energy is conserved. In addition to elevation and kinetic energy, we are seeing that pressure energy is also being conserved, right? Some of them is conserved, not like one of them. So elevation is what? Or potential energy is what? Potential energy is mgh plus kinetic energy is what? Half
Half m.
mv square plus pressure is what? Pv, right? P into volume, right, equals to constant, right? So let me just rearrange this to being at the front and elevation at the back, because that's how it's always written. P into V volume. Let me just write it volume instead of V, because that will make it confusing with velocity. Plus half mv square plus mgh equals to constant, right? So let me just divide everything by mg. So everything divided by mg will become, so it will become PV divided by mg plus this one half mv squared divided by mg plus mg is divided by mg will be h equals to constant. So mass divided by velocity, volume. So if I bring volume here, mass divided by volume, what will be that? Mass divided by volume is what? Rho.
Density.
Rho
Rho.
g. Rho, yes, exactly, density. Mass per unit volume is the rho. Plus if I cut this one, so it will be v squared divided by 2g plus h equals to constant, right? So this is basically Bernoulli's equation. Bernoulli's equation actually is not derived like this. This, for your understanding, I've shown you that it is law of conservation of energy. Rather, Bernoulli's equation is derived by doing like force balance on one stream of liquid and then conserving the forces. So you don't have to know that for this class, right? Just know that this is the Bernoulli's equation, and here we are showing that energy is being conserved. So this rho g, it has a it has a name that is called gamma or specific weight. Or it is saying that weight divided by what? Weight divided by what will be that? Weight divided by volume. Weight is what? Mg, right? Mg divided by volume. So m divided by volume is density. So density into g. So density into g, we can write that as P divided by gamma plus V square divided by 2g, plus instead of writing h, it is fancier to write z equals to constant. So we have derived our Bernoulli's equation. We have derived our Bernoulli's equation. So this is called what? What is the name of this gamma? Specific weight.
Specific weight.
Yeah. So this called pressure head. So what is head? Head is basically saying express energy in terms of height, that is called head. So when you express energy in terms of height, let's say mgh, instead of writing mgh, if you write just h, you are expressing actually energy in terms of height. So that is basically the head. So the unit here for all the unit here for all the terms will be actually length, units of length. This one will be in meter or centimeter or millimeter, whatever it is. If you do dimensional analysis, if you actually derive the units of v square divided by 2g, it will be in meter. If you just derive the unit of pressure divided by specific weight, it will be also in meter or centimeter or whatever the length is. So if you express energy in terms of height, you get head, right? This is basically more convenient to work. That's why we have named this new term. So this called pressure head, this called pressure head, this called velocity head, and this is called elevation head. Clear, everyone?
Yes, sir.
So this is basically the Bernoulli's equations. We have three heads in Bernoulli's equations. One is the pressure head, P divided by gamma, that is P divided by specific weight, then V square divided by 2g, or velocity divided by head, and then the elevation head, or Z, right? So we are done with deriving Bernoulli's equation. Now it's time for us to apply those Bernoulli's equation, right? So before that, let me tell you something. If you, let's say, have this channel, if you have this channel, mm, if I say we have studied that mass is energy is conserved. Now we will say that mass is conserved. You already know this, right? Mass is always conserved. So if I say I have 1 liter of water flowing here in, let's say, 2 minutes, or 1 kg, let's just make it easier for you to understand. So how many kg of water will come out of this tunnel? Let's say this is like filled, it was previously filled with water, and you are letting 1 kg of water in 2 minutes. So how many of water will come out in 2 minutes?
So 1 kg.
1 kg. Because water will not get accumulated here, right? Because it has like it all the thing that you will be giving in from one side, it will be coming out from the other side, right? So can I say that mass per unit time at inlet equals to mass out per unit time? Can I write this?
Yes, sir.
So mass is what? Density equals to mass per unit volume, right? So can I write mass as density into volume? So
Yes.
mass is density into volume in, density in into volume in divided by time, equals to mass out will be density out into velocity out, volume out divided by time. So if I say it's incompressible, the fluid is incompressible, that means the density of the fluid density equals to constant. So density in will be equals to density out, right? So I can just eliminate this term because the fluid is incompressible and density, these two densities are same. So can I just say volume of fluid in divided by T equals to volume of fluid out per unit time? So we are saying that volume of fluid in per unit time is equal to volume of fluid out per unit time, and they have a special name for it that's called flow rate. Flow rate, and it's represented by Q. So Q is basically volume of fluid divided by time. That's basically saying what is the volume of fluid flowing per unit time. So clear what is flow rate?
Yes, sir.
Flow rate is nothing but the amount of fluid that is flowing in per unit time. Or if you have, let's say, a tape here, if you have a tape, water is coming out. This is basically saying what is the amount of water that is being coming out, right? So that's how you calculate the flow rate. So now you know flow rate. Let me extend this term a bit. Let me go here. So what is volume here at this section? What is the volume? What is the volume here? What will be the volume? Can I just say volume is this area, and let's say this length, let's say the area is constant. Can I say that volume equals to area into length?
Yes, sir.
Yes.
The pi r square into d.
Yeah, let not just go to pi r square. Yeah, pi r square into L. Yeah. So we can write this here as volume is equals to area into length divided by time, right? So what is this length divided by time? What is this length divided by time? You know.
Velocity of fluid.
Yeah,
Velocity.
yeah, exactly. So Q is equals to area into this length divided by time is the velocity of the fluid. Velocity of the fluid, that is how fast the fluid is flowing. So this will be Q equals to area into velocity. Clear everyone? This is an important formula, that is flow rate equals to area into velocity. Any question about this term? So how, let me just give you some examples. So if you have this like nozzle, let's say this one is 0.1, this one is 0.2, right? So this one will be area 1, this one will be area 2. Now you are giving in some fluids here, and the fluids will go out through here and they are incompressible. So which area is greater? Area 1, right? Area 1 is greater than area 2, right?
Yes, sir.
Yes, sir.
This nozzle cannot create water. Let's say water is flowing, this nozzle cannot create water out of itself, right? So all the water that's coming in must go out, right? So the flow rate or mass flow rate must remain constant. So since the area is more, we know Q equals to the flow rate must be constant. All the water that's coming in must go out, so Q must be constant, area into velocity, right? Since the area is more, what will happen to the velocity?
It will decrease. It will be less.
It will be less. Or if I go from point 1 to 2, area 2 is less than area 1, right? It's basically writing this here. So as the area is decreased, the area is decreased from here to here, what will happen to the velocity?
The velocity will increase.
So v2 is greater than v1, right? V2 is greater than v1, the velocity is increased. Can you give me one practical example of this phenomena? Every one of you have observed this one. I can guarantee this. Can you give me one example?
Sir, body square.
Yeah.
Body square.
Not kind of body spray uses other principles in addition to this. There are like much something that you see every day, you see every day. uh, okay, water coming out of tap. So let's say, or water coming out of a nozzle, let's say this one is the nozzle. I'm not good at drawing. So water will be coming out, right? If you just if you just block some part of the nozzle, if you just block some part of the nozzle, what will happen? The remaining fluid that will be flowing out much faster, right?
Yes, sir.
So let's say uh, you are what, you are watering your garden, right? Or you are just, you have a large pipe at your hand, and you will be throwing water at your flowers in the garden, right? So initially, if the water has like less velocity, what you do, you just squeeze the pipe, right? If you just squeeze the pipe, what you are doing, you are basically decreasing the area, you are decreasing the area. When you are squeezing the pipe, you are decreasing the area. What happens when the area is decreased? You see that like the sprinkles of the water goes much further if the area is decreased, so the velocity is increased, right? Or in tap, if you just let the water flow continuously, you will see that the water is falling slowly. If you just what, if you hold part of the tape with your hand, you will see that the remaining part will actually, the water will flow at more much greater speed, right? So we have learned up to this. So do you have any confusion up to this, any questions?
No, sir.
No,
So
sir.
we have learned Bernoulli's equation. Let's go back here and take what we have learned. So we did learn, did you learn, not me, did you learn Bernoulli's equation? Yes or no? Just tell me yes or no.
Yes, sir. Just now.
Yeah. Specific weight.
Yes,
Yes,
sir.
sir.
Specific weight is the gamma thing. Head is basically
Yes,
representing
sir.
energy in terms of what, in terms of height. Continuity equation, continuity's equation is nothing but mass flow in equals to mass flow out, or q in is equals to q out. And you know what is q? Flow rate. What is flow rate? Flow rate is area into velocity or volume of fluid per unit time. So you learned continuity equations, right? Now, applications of Bernoulli's equation. I will be showing you one applications of Bernoulli's equation. So let's, do you know how airplanes fly?
No, sir.
Uh, there is something called airfoil, and it looks something like this. The wing section. This is basically part of the wing. The wing looks something like this, right? Or wrong? It's a law. It's a very, so let's say this is the plane, and these are the wings. So this section of the wing is called an airfoil, and this is this is called an airfoil. That is the cross section of the wing. So you see the air particles will be moving at the top, and air particle will be moving at the bottom too, right? these are the air particles that I'm showing. These are the air particles. So if a air particle has to move from here to here, if an air particle is to move from here to here, which distance is greater? This distance is greater, right? Because this is slightly curved and this is straight, right? So
Yes, sir.
this is called like upper one. This is, let's say, the bottom one. So this is the bottom one. So upper section has greater length. So what will be the value? It will travel at the same time. So what will be the velocity at this section, at the upper section?
More.
Velocity will be more because it has to travel more distance. Since the distance is more, the velocity will be more. What will be the velocity of the air particles here? Velocity of the air particles here, the velocity will be less, right? So what do we know from Bernoulli's equation? P1 divided by gamma plus v square divided by 2g plus z1 equals to constant, right? So if the velocity is more and the elevation is almost constant for both these terms, so z is, we can like neglect this. So if the velocity is more, what will happen to the pressure? And whole thing is constant. If the velocity is more, the pressure will decrease,
Yes.
right? The pressure will decrease. If the velocity is more, what will happen to the pressure? The pressure will decrease. Since the velocity is more, the pressure will decrease, right? And let's go to the bottom section. At the bottom section, since the velocity is less, I'm using blue for the bottom section, or green for the bottom section. If the velocity is less, what will happen to the pressure?
Pressure will be more.
Pressure will be more. The pressure will be more. So you see the pressure at the top, is less and the pressure at the bottom is more, right? So you have this plate where the pressure is less at the top and pressure is more at the bottom. So in which direction this plate will move?
Direction.
Sir, upwards.
Upward direction, right? It will move in upward direction. So this is called generating a lift. This is called lift. This is basically how a plane flies. You see those big engines here, or
Sir.
the propellers,
Yes, sir.
the basically the task of the propeller or engine is to let the airflow in, nothing else. Is just to cause the airflow at the top and bottom of the airfoil, nothing else. So you are using those engine just to bring air, right, to the airfoil, and it is this shape of the airfoil that is actually generating the lift or the upward thrust. The engine itself doesn't produce a thrust.
Sir, how the engines help to flow the air?
Okay, that is we have one class on engine. We can discuss that in that class because that is a completely different concept from what we need or what we are teaching here. It's basically burning, and when it's burned, it creates vacuum. The turbine, it has very low pressure. The turbine that is being discussed in our last class, it has very low pressure. When it is at very low pressure, it will basically suck air in. This is one of the principle at how lift is generated at the airfoil. So this is one of the applications of Bernoulli's equation. And another one, all the rockets uses something called converging diverging nozzle, and it is something like this. Converging, this part is decreasing, that's why it's called converging, and this part is increasing in area, that's why we call it diverging. So converging diverging nozzle. This is I'll be giving examples of Bernoulli's equation. The second example will be here, and also this one is directly related to our experiment. So okay, clear about the airfoil thing, everyone?
Yes, sir.
Yes, sir.
If you have any confusion questions, you can ask me now. I'll try to like help if it is related to this class. Okay, I think you have no questions. Let's move on to the next one. So you have this three section 1, section 2, and let's say section 3, right? So let's talk about what are the two equations that we learned. Q equals to flow rate. Flow rate is equals to what? Volume of fluid per unit time, or area into velocity, right? And the other equations that we learned is P divided by gamma plus V square divided by 2G plus Z equals to constant. This is the summary of our today's class. So we'll be applying it in this converging diverging nozzle. So you see from section 1 to 2, what is happening to area? Area is decreasing, right? As the area is decreasing, as the area is decreasing, what will happen to the velocity from section 1 to 2? See,
Velocity will increase.
yeah, velocity will increase. See, the section, you can see the section, the area is decreasing, right? Since the area is decreasing, what will happen to the velocity? Velocity will increase, right? So we can say that as area is decreasing, velocity will increase. So as the velocity is increasing, what will happen to the pressure in this equation?
It will decrease.
Pressure will decrease.
Pressure will decrease. Pressure will be decreased. Yes, pressure will decrease. So this is one part. This is the what part? Converging part, right? Let's go to the diverging section. From point 2 to point 3. Point 2 to point 3, what will happen to the area? Let's say this one is from 1 to 2. Let's go from point 2 to 3. What is happening to the area?
Increasing.
Area is increasing. As the area is increasing, to keep the flow rate constant or the mass flow rate constant, what will happen to the velocity?
Decrease, sir.
Velocity will decrease. Yes.
Yes,
So
velocity will decrease.
if it is actually going through an expansion, you see it is going through an expansion here. When it's going through an expansion, the velocity will decrease. If it is going through an contraction, the velocity will increase. The contraction and increasing velocity, that is like the tape is the best example. If you just hold part of the tape, you will see that the fluid that's coming in out will flow at much larger speed. So you can just try it out today, like in your washroom. So as the area is increasing, velocity will decrease, right? As the area is increasing, velocity will decrease, right? So as the velocity decreases, what will happen to the pressure? As the velocity decreases, what will happen to the
Pressure will increase.
Pressure will increase. So let me draw something. This is called pressure profile. From this section to this section. Let's say this one is section 1, this one is section 2, and this one is section 3. So what will happen? Let's just draw velocity at first. So velocity will increase from here to here. Velocity will increase and then velocity will decrease, right? So velocity curve will be something like this, right? Do you agree?
Yes, sir.
Velocity will increase. Velocity increase because it's passing through a contraction, and then velocity will decrease because it is passing through an expansion. The expansion is here, right? So what will happen to the pressure? What will happen to the pressure? Pressure will at first from here to here, pressure decreased, right? From 1 to 2, the pressure decreased, right? The pressure decreased, and then what happened? The pressure increased from 2 to 3, right? Pressure will be something like this. Clear, everyone, about this graph?
Yes, sir.
Yes, sir.
Let's say this is velocity head, this is pressure head. So total energy, that will be the sum of velocity head and pressure head. That will be somewhere, something here, right? It will be something here, and it will remain what? Constant. Like, clear about this part? Total energy, that is basically the sum of these two, the sum of these two, the sum of these two. Their sum will remain constant. That is the total energy, right? This total energy line, that is called energy gradient line. And the one about the pressure, that is called the pressure hydraulic gradient line. Clear? The one with the pressure, it's called the hydraulic gradient line. The one with the total energy, that is called the energy gradient line. So how can you get the velocity from these two lines? If you just subtract the pressure from the total energy, if you just subtract the pressure from the total energy, you will get the velocity, right? From the velocity, you can calculate the what velocity gradient line, or there is nothing called velocity gradient line actually. Clear about this part?
Yes, sir.
So we are almost done with everything. Let's go to the top and see. So you are done with applications of Bernoulli's equation, right? I didn't show you the experimental setup yet. You are done with hydraulic gradient line, energy gradient line, and all this. So experimental setup. For the experimental setup, it's this is what the experimental setup looks like. So let's go from the start. So you are giving some water. Water is flowing from here. This is the water inlet, and water will flow through these sections. Water will flow through these sections. Water will flow here. Water will flow here. Does this section look familiar?
Yes, sir.
This is what?
The converging side.
Diverging nozzle. Yes, this is the converging diverging nozzle. Yes. So we have this converging section here, and we have the diverging section here. So you already know what will be the velocity profile and pressure profile of this converging diverging nozzle, right? So let me draw that again here. What will happen to the velocity as it moves through the converging section, this section? What will happen to the velocity? What will happen to the velocity? As it, the velocity will increase, and up to here the velocity will increase, and then as it passes through the diverging section, the velocity will decrease. This is the velocity. What will happen to the pressure? Exactly opposite. Exactly opposite, nothing else, right? So the pressure will decrease, and then the pressure will increase. So this is the experimental setup. First of all, you will flow some water through this section. You have to find out the flow rate. You have to find out the flow rate. So how you are going to find out the flow rate? Flow rate is what? Volume per unit time, right? Volume per unit time. So see, we will have a tap here. So water will flow through this tap, or that is called venturimeter or orifice meter. There are different type of flow rate measuring devices. If it were in lab, I would be showing you how each of them works. So let's just say it is a tap, simple tap, and you will turn on the tap, and you will correct specific volume of water in, let's say, 1 minute. In 1 minute, let's say you have collected 5 liters of water, right? You turn on this tap, keep it on for 1 minute, and then check what is the volume of fluid that you have collected. From there, you can calculate this flow rate, right?
Yes, sir.
And then your next task will be find the area of each of these sections. There are 11 sections in total. You have to find out the area of these sections. These sections, if it were in lab, I would have been showing you how this works, but since we are not there, you have to go with the imagination. So you have to find out the area of each of these sections. So you know the flow rate. Flow rate is equals to what? Area into velocity, right? And you know the flow rate from here. You know area from here. You have to measure the area. Can you find the velocity?
Yes.
You will be able to find the velocity. So if you connect the velocity of each of these sections, of each of these 11 sections, and draw a graph, you will be getting a graph like this. Everyone use your imaginations. So what you have basically found this line, right? You have found this line. So how to get this red?
The bottom
How-
part of the screen.
Oh, sorry. Yeah. So you basically got this part, right? You got the velocity line, and how to get this pressure line. So let's say you have some water here. You have some water here. What will be the pressure here for this water? What will be the pressure here at the bottom?
0.
No.
Highest. Pressure highest.
What is the pressure? There is a formula.
H
Del
rho
P.
G.
H rho G. Exactly. Yes. Pressure will be H rho G. Del P is the H rho G. That is what the pressure is being applied by the mass of this liquid, right? The mass of this weight of this liquid. So what is the weight of this liquid? Mg, right? Mg, weight of this liquids, and pressure is what? Force. Pressure is force per unit area, right? Mg divided by area. So M is what? Density into volume. Density into volume into G divided by. This is, I'm showing the derivation for those of you who couldn't actually tell me why pressure is equals to H rho G. I'm showing the derivation. So pressure equals to force per unit area. Force is what? The weight of this particle. The weight of this particles is mg, and area is area. So what is mass? Mass is density into volume into g divided by area. Rho into what is volume? What is volume?
L into H.
A into H.
Area into height into g divided by area. So let's this. So what we get? Rho g h. Clear, everyone?
Yes, sir.
So rho g h. So if I go here, what is the velocity of the fluid? Fluids are moving in x direction. They do not have any y direction, right? The y component of the velocity is equals to 0. So the fluids cannot go to the top, but the fluids are going at the top. Why is that? Although the velocity component at the top sections is 0, the fluids will be going at the top. Why is that?
There is a pressure difference.
Because of the pressure. Yes, we have a pressure, right? H rho G. So we have the pressure here, but we do not have the pressure at this tube, right? Let me show it here. You have this pipe. Water is flowing here, right? So some of the water, it has the velocity, y component of the velocity is 0, but still some of the water will come here. Why is that? Because we have some extra pressure here. This extra pressure is because of this H. Extra pressure is because of this H rho J. So because of this extra pressure, the fluid will go at the top. We have a instrument for measuring that is called a piezometer. So what this is basically a piezometer. Due to pressure build up, the fluid will move at the top. So if the fluid is moving at the top, if the fluid is moving at the top, you will get the fluid, you will get, you will have to measure this up to what point the fluid has moved in this pipe. This is the, this will be the point at which the fluid moved up the pipe. Clear why the fluid will move up the pipe? Or do you have any
Yes.
conflict? The fluid will move up the pipe not because of the velocity, they will move up the pipe because of the pressure. Some extra pressure is being created here, because to relieve the pressure, the fluid will move here. So the fluid moved up the pressure line. So if you just measure each of this line, does it look something like this? Does it look something like this? This one, does this line look something like this?
Yes, sir.
Yeah. So you will be connecting these lines. You would have measured this in the, you would have seen this and taken the reading and then connect this in a graph, and you will be seeing a figure something like this, right? So if you just combine these two, ideally you would have gotten something like this. So this is called, what is the name of this line? What is the name of this line?
Energy gradient line.
Yeah. So if you connected this line, you will be getting something like this, energy gradient line. You'll be getting something like this, right? So but realistically you will be getting a line that is something like this. Why is that? Why is that? So this is not ideal scenario. Are you seeing the screen?
Yes, sir.
Okay, please respond, otherwise I thought that I lost my connection. So this is not ideal scenario. There will be some energy loss. This amount is the energy loss. There will be loss from the top to the bottom. Since the energy decreased, what will happen to the total energy line? It will go down, right? Energy loss, this is the energy loss. And you are not supposed to quantify this in these experiments. In our later experiments, when we will be doing pipe friction, we will actually find out the exact amount of energy that is being lost, right? In that experiment, you will be seeing the quantity of energy, you will be finding out the quantity of energy that is being lost. And this is the hydraulic gradient line. You already know water piezometer. So clear about this experimental setup?
Yes,
স্যার
sir.
স্যার ব্লু কালার লাইনটা দিয়ে কি বোঝাতে চাচ্ছেন, মানে এটা ডাউনওয়ার্ড যাবে কি স্ট্রেট লাইন না থেকে?
Yes, the blue color line will go down instead of being straight, because energy will decrease. দেখো এখানে ফ্রিকশন আছে, বুঝছো? অলসো there will be more losses. ফ্রিকশনের লসটাকে আমরা বলি মেজর লস, আরো কিছু কিছু লস আছে এই টার্ন। Loss, what will happen to the total? Can you hear me now?
Yes, sir.
Yes, sir.
Oh my God. From where did you lose me?
So last 5 minutes.
From where? Can you just tell me? I don't know what I've discussed in the last 5 minutes. What is the last thing that you have like seen or heard?
Energy loss.
Okay. Let me discuss this thing. Just you could have just unmuted your mic and told me I'm not seeing this chat. So you could have just unmuted
Oh,
your
okay.
mic
Sorry, sir.
and
Sorry, sir. Next time.
told
think about it.
me
Okay, sir.
that you are not getting me. Uh, so you are clear about this part, right? The how to do the experiment. Let's just go here and see. So you will collect.
Have you shared your screen share?
Sir, the screen is blank.
Okay, thank you again. Sorry. Can you see it now?
Yes, sir.
Yes, sir.
Thank you again. There are a lot of things to deal with. I like the physical class. I don't like this stuff. So you are like clear about this part, right? Uh, the energy gradient. Please respond. No one is going to kill you. Uh, you are clear about this part. The energy gradient line, the hydraulic gradient line, right? So first thing, you have to collect some volume of water in some specific time. You have to write it down here. What is the volume of water being collected and what is the time, right? From these two, you can find the flow rate, since flow rate is volume per unit time. So this is how it's being done. You will be collecting some volume of water in a bucket. You will use stopwatch and then find the flow rate. And then you have to measure the cross-sectional area of each of the sections. You'll have to find these cross-sectional areas, and you like in experimental setup you could have done it very easily. It's much easier done than being said. And then you have to find the velocity. How to find the velocity? It's basically the flow rate. You have measured the flow rate here per unit area. You know the area, so you find the velocity. From the velocity you can calculate the velocity head by velocity square divided by 2g. So you know what are velocity head. That is basically expressing what is the amount of energy, kinetic energy, right, in terms of height. And you have to find out the piezometer head. How to find the piezometer head? These are the piezometers. There will be some markings. You will see where the water went. The water will move up the piezometer, and you can find the piezometer height from there. So you know the piezometer head. So you know the velocity, you know the velocity head, you know the piezometer head. You can add these two velocity head and piezometer head and find the total head. Can you do that?
Yes, sir.
Sir,
Yes,
yes.
sir.
So total head will eventually decrease. And that is the task of this thing here. So you have to draw a total head graph, and you have to draw like how you have to, in a graph paper you have to draw for these 11 sections what are the total heads, right? You can do that. That's very easy. And then you have to draw this like pressure head plus elevation head. Elevation is head is almost constant or zero, like just the pressure head. What is the name of the pressure head graph? That is the hydraulic gradient line. So you have drawn the energy gradient line, that is the total head, and you have drawn the hydraulic gradient line, right? So, and you have to discuss what are the variations of why there are some variations in the total energy line. If you have drawn, you would have seen it. This basically this. Okay, let me just not go there. It will be hassle. And then you have to discuss what are the effect of friction. The total energy line will be slanted downward a bit as I have shown you, and you have to discuss that. And then you have to discuss what are the sources and effects of errors in the measurements. So while you will be doing the experiment physically, we will see that there are lots of scope for errors. Like I have discussed while seeing the piezometer head, there can be parallax error. While measuring the time for the collection, there can be a reaction time error. There can be some spill while you are collecting the volume of fluid. There can be frictions. Like there are lots of there can be lots of sources of error, and you have to discuss them. So clear, and there are some assignment questions. You have to do the assignment and submit it before the next experiment. So let's just discuss to the things that we are supposed to go to the things that we are supposed to discuss. And here, so you have seen the experimental setup. Are you clear what is a piezometer?
Yes, sir.
What is a hydraulic gradient line? That is basically the pressure connecting all the pressure is called the hydraulic gradient line. Do you know what is energy gradient line? Yes, that is the total energy. Do you know like how the data table look like? Yes, you know, I think. And then you have to submit the lab reports before the next experiment. So clear, everyone? Any questions?
No, sir.
No, sir, not yet.
Specifically about this. This is let me summarize some of the important concepts that we have learned that I think you should remember. Firstly, some of the concept that you must remember is these equations, and then what is flow rate. Flow rate is what? The amount of volume of fluid per unit time, and is equals to area into velocity, right? And then the continuity equation, that is mass flow rate in equals to mass flow rate out. These are the some of the important concepts, nothing else. Clear about this part?
Yes, sir.
Yes, sir.
If you are clear, I think I can stop sharing my screens, and if you have any questions you can throw it to me now.
Sir,
Yes.
from the experiment, how
Yeah.
can I find the piezometer?
You didn't understand the piezometer.
I understand how, but I don't know how can I find it.
How can you
Find it.
find it?
Yeah.
A piezometer is basically one, you have seen test tube, right? It's basically a type of test tube where at the bottom the fluid will flow, and then the water will rise at the test tube, and there will be scale for you to measure the amount of water height, right? And then from that height you can actually take the readings of water readings, and the water that will rise in that piezometer is because of the pressure only. So that is basically the pressure head.
Sir, can you check the screen from the data,
Okay.
the table data?
Okay. Uh, Data, this one you are talking about.
Okay. Yeah. How can I find it?
This is this
The value.
these readings, the like you will see the water here, you will see water here, you will see water. This is basically the water line. So the piezometer head at this tube will be this water line. Piezometer head at this tube will be this water line. I think that's why I'm saying like there is no point actually doing these experiments here. If these are basic, how do I explain it to you? These are basically some tubes. You will take readings from those tubes. You will be seeing the water here. I don't know how to explain that. So you will be seeing the waters here. You will be taking the water readings from here. You will be taking the water readings from here. Clear?
Yes, sir. I understand the experiment, but to do this data or to put the data, I don't know how. Where can I get to put it?
So you get the piezometer head. The piezometer head is basically the pressure, right?
Yes.
Pressure equals to what? H rho G, right? So we are not dealing with the actual pressure. Instead, we are dealing with the head. So H rho G, head is basically only the height. So you will just write the height here, the centimeter or millimeter, whatever it is. You will just write the height here. You will do it for 3 different flow rates and write it here eventually. Any questions?
Sir, will we be provided with data for completing the experiment?
How you are going to complete the experiment? Like I can give you the data, but there is no alternative to actually seeing this.
Yes, sir.
You will be taking these readings, this piezometer height, the flow rates, and then seeing this setup. I'm not sure how it's being done in the other group, like group 1 and group A and group C has done the experiment, I think. Did they get the data? Do you have any idea about that?
No, sir, not yet.
No,
I'll ask
sir.
them.
I can provide you the data if that's what other people are doing. But there is actually no point in doing the data. But for sample calculations, I've given you some sample calculations here. I'll be giving you this PDF. There is a sample calculations. Once you do the sample calculations, if you actually answer these assignment questions, you will get a pretty good idea of what's going on. And then actually once I show you the experimental setup, let's say for just 5 minutes, and then you will get everything. We have like 5 minutes of experiment that's we need to do, just seeing this setup, nothing else. So let's see theory. So Bernoulli's equation is applicable only for steady incompressible flow. We said the density is constant, right? That's why the incompressible flow. Otherwise we have to derive a whole lot of other sets of equations. We didn't do that. We have said the density is constant, so it is incompressible flow. Steady, what does steady means? Steady means it's not changing with time, nothing is changing with time, right? Everything is like happening as it happened before. Let's say in the last before 1 minute, it was the flow rate was 1 minute per second, is still the 1 minute per second. If there were some changing of flow rates or changing of velocity, changing of head, you can say it give rise to some error. So while you will be doing the experiment, you will be seeing the piezometer head will be increasing and decreasing. It will be like it's not constant, it's oscillating, it's oscillating. So that is not steady. That is a source of error in the experiment. You can write that in the discussion part. I hope you will remember this when we are doing the experiment, so that you can write actually this, or you can just write these stuffs now, take a note. I don't know what you are doing. And this applicable for in viscous regions. In viscous regions is basically where there are viscous force. So what are viscous force? Viscous force are basically the frictions within the fluid. It is basically saying why honey falls lower than water, right? Honey is stickier than water, so honey has more viscosity than water. So we'll be ignoring this term altogether, because if we involve this term, it will add more complexity. So if you say that, if you see some error in the experiment, you can tell that it's because of the viscosity in the inherent viscosity in the fluid. So as we said, the net viscous force is negligibly small, and these are some things. So you are clear about this. P1 divided by gamma. Gamma is basically rho g, or density into gravity, acceleration due to gravity. That is called specific weight. V squared divided by 2g. This is the pressure head, this is the velocity head, this is the elevation head, and sum of the head is constant. Pressure head, velocity head, elevation head is constant. These are the way of writing Bernoulli's equation. Total energy at one point is equals to total energy at another point, plus some head loss. Head loss is because of the reasons that I have discussed, because of the unsteady term, incompressible fluidity, viscous force, and lots of frictions, those stuffs. And then the experimental setup. Clear, everyone?
Yes, sir.
Do you have any questions? Any more questions?
Sir, can you repeat the concept of elevation head? I didn't get it.
Elevation head is basically what is potential energy, mgh, right? Potential energy is mgh, right?
Sir.
So writing energy in terms of head, writing energy in terms of length, sorry, writing energy in terms of length is called the head. So mgh, right, divide by that mg, what you are getting, h, that is called the elevation head. It just writing energy in terms of length is called the head, nothing else. Whatever the energy. So for velocity, it is v squared divided by 2g, right? You have the velocity or kinetic energy, you want to convert that to what? You want to convert that to head. So you do v squared divided by 2g. If it is pressure, you know the pressure of the fluids. So what will be the head of that fluid, head of that energy? It will be P divided by rho g, or P divided by gamma. if you know the potential energy mgh, what will be the head or energy in terms of length? That will be h, just h, right?
Yes, sir.
Any more questions?
No, sir.
Did anyone by chance record this class?
Yes, sir.
uh who did? 07.
Yes, sir.
Okay, can you mail me the recording after the class?
Okay,
You did it from PC or from mobile?
oh, sir, from PC.
Okay, can you send me the recording after the class?
Okay, sir.
I think Sadman. What is the ID of Sadman? 11.
Sir, 211.
Okay, 11 has my email ID. Do you have my email ID?
Sir, I'll have to check.
Okay,
I arrange for it.
okay. If you don't have any questions, if you think everything is clear, I think we can end this class right now.
Okay, sir.
Okay. Just in case if you face any difficulties while doing the